Okay, good morning, and this is Peifan, and today's my title is Metropolitan-scale mobility digital twin. And first, let me give a brief self-introduction. And I'm Peifan, and I'm currently an adjunct project lecturer in the Center for Spatial Information Science in University of Tokyo. And also, I'm a senior researcher at a startup company of Location Mind in Japan. And my research was specialized in the human mobility modeling. And for the startup companies I'm working in is Location Mind. We are the startup company that from the Shibazaki laboratories in University of Tokyo. We have applied our technologies to different spatial related projects in Japan. And having some project like the people flow, big data processing, and the analyze and visualizations of the people flow, and also for the people flow predictions, and also some security problems in the positioning signals. Okay, so so let me start my talk today. And for the mobility digital twin, actually, here is a simple visualizations of how mobilities in the physical world look like. People are moving in the city, they are walking, or they are taking the trains or using the cars, and this is how it looks in the physical world. And using with the development of the IoT or the smartphones, and we can collect the human mobility status in real time. Here is some visualizations of how people moves in Tokyo, and it is on a very special day. It was the Tohoku earthquake in Tokyo, and now it has not been. It is a normal day, but in the afternoon, maybe later, you can see how the human mobility is responsive to such kind of big disasters. Okay, so here, now the earthquake happens, and at that time, all the public transportation is down. And actually, it is a typical Friday, and many people are at their workplace, and they have to walk back to their home. So that is how the mobilities we can sense and we can collect and visualize in the digital world. So for the full pictures of mobility digital twins platform, it looks like this. For the physical world, we have the mobilities in the real world, and having different ways of sensing the human mobilities, and also some other environmental factors, like using some deployed sensors, or using smartphones, or using some crowdsourcing way, or using the surveillance cameras, or the location-based social networks. And then we can have digital replica in the digital world, and having some pre-processing of the data, and also to construct the trajectories database, and then to have the replica of the mobilities in the digital world. And based on the replica of the mobilities, we can further making the predictions or making the what-if simulations, for example, under different scenarios, like a big disaster or some bad weathers, and how, if that happens, how the humans' mobilities will in response to that kind of conditions. And based on that, we can do the policies or finding of the good control policies that can be applied to the city. And for the existing mobility intelligence systems, for example, for the traffic predictions, mainly analyze human mobilities in an aggregated form. For example, in many existing research of traffic predictions, the mobility is aggregated in the grid cell, or it is mapped to the road network, or using some loop detectors to detect the cars in the road networks. But they do not have the origin destination information, and the spatial granularities is not very good, or they are more focusing on single modalities of the human mobility. For example, on the road networks, we can only sense the human mobilities that's using cars, and the people's, for example, for walking or using trains, we cannot have such kind of informations. And if we want to make the simulations or for the predictions of the human mobilities, for example, 1 hour ahead, if we want to predict the traffic, maybe at the current time, most of the people are not on the road. They may be in the office, or they may stay at home, or they may travel in a train. They may having the other modalities of the transportations. So in that way, we cannot having a full pictures of the city mobilities, and we cannot do a good prediction or simulations of the traffic. So here it shows most of the existing mobility intelligence systems look like, and we can collect the different kinds of trajectory data or other sources of mobility data, and aggregate it to the traffic, like in on the outflow or passengers count or car countings, and then building spatial temporal predictive models that to predict the future aggregated traffic, like the traffic speed or traffic volume. In our works of we want to build more real replica of the mobilities in the city. So we do not aggregate the traffic in the first step, but we want to predict each agent or each users in the cities. We want to predict their future movements of each individual, and then for any task of traffic analysis, like the traffic volume or traffic speed, we can aggregate it in the later step. Then it will not lose it will not lose informations in the modeling part, and we can have a more full pictures of the mobilities in the city. Yeah, and so in this work, our objective is that our mobility's digital twin system can answer the questions like, for example, what the traffic flow on a specific road segment. It will not be a grid, or it will have a very good spatial granularities, and also how the passengers will transfer in interchange stations, like in the Tokyo stations. Here is our prediction result. For example, when people taking a specific lines to Tokyo stations, we can predict how their next trains will take, or whether it will just leaving the stations. Such kind of different choices in their next transportation choice can be also predicted. And also, we are not predicting only the traffic volumes, but we can know that if we predict, for example, here the traffic, there will be an increase of the traffic. We also know that the future arrivals come from, where these future arrivals come from, and how they will get to the destination. So in that way, we can have a better view of how we can control the mobilities, or how we can intervene to do the interventions of the mobility if we want to prevent the future growing of the traffic. And and also we can do the simulations of how people move if some specific train line is stopped. We will show these results later. And so the main approach we are using is more stratified modeling. For more actually, in the mobility modelings for an AI model, I think there are mainly two branches. One is more data-driven approach, like we make each locations as a kind of word. And then the mobility prediction task is just like predicting the next word prediction. And another branch is a more rule-based or agent-based approach. Like we can search from their origin destinations shortest paths, or we can having utilization functions to simulate the people's movement. And in that ways, it is more it will can be suitable for more mobilities that with the constraints of the transportation network. For example, we have the railway systems, and we can simulate how it can transfer at the stations. And but in this way, it is difficult to be trained in an AI model because the constraints is very complex, and so there are many constraints. It is difficult to be combined into a data-driven model. So we are using two levels modeling that we model the humans' mobilities. At the lower levels, it is more close to the raw GPS trajectories, and it is more constrained with the local transportation facilities, like the railway or road network, transportation network. And at the higher levels, it is more bigger levels, larger levels, like the class, we call it the cluster levels mobilities. Like we are staying at this region, and maybe 1 hour later we'll go to another regions, and in that level, the data can be more easily to be modeled as the data-driven model. And at the lower levels, like their details, routings, it is more easily to be modeled at a rule-based level. So we make these stratified models and model the mobilities in the two level. And from we do the trip segmentations and the mode detections and the map matchings to precise with raw GPS trajectories to the node level trajectories. And so it will having the more semantics informations of the trajectories. It at a very large scale, it is difficult to be models in the real time. So we make it more, we make it precise in the offline manner. And also for the raw GPS data, it will having a high uncertainties. For example, if we observe the 3 right points, it is very difficult to know that whether this trajectory is whether this user is travel in the black road or it is travel in the blue road. And after we collecting the green point, we can know maybe it is more likely that it's travel in the black road. So such kind of uncertainties, it is also very difficult to model in the real time. So for this part, we mainly model in the offline manner. And for the cluster levels, we predict the our main task is to predict their destinations region. It is a more cross level. For example, we observe users' trajectories, and we want to predict 1 hour later where their destination region it is. And then using such cluster levels prediction, it will be used to determine the node levels trajectories. Actually, it is quite meets with our moving behavior. For example, if we are thinking of going to places, maybe we are first thinking our destination. For example, like going to the Raffles City or going to the NTU universities. Such kind of destinations is first determined by ourselves, and then we can plan our detailed routines. Like, for example, which stations or which roads should I go? So our modeling is also following these intuitions that we first predict the destinations using an AI model, and then refine it using a predict by retrievals frameworks that to find out most suitable routings for these users from the historical database. So the 2 key problems is how we can predict more accurate class levels prediction, and another problem is how we can refine the cross levels prediction to fine-grained. And for the cluster level prediction, it is more like a next word prediction, and but it is conditioned on the current city state. For example, if the current city is a work day, then it is more likely the user maybe go to the workplace. If it is weekend, the user may be more likely to go to a shopping mall or such kind of entertainment places. And so we use, there are many solutions for such kind of encoding the city state. One ways we worked is using the crowd context predictor that encode the crowd context that using a vector representations of the city's current state. Like if here is 1, then maybe the city is more related to the working day, and the commuting patterns of the users will increase. Such kind of vector representations will be more easily to be used for the crowd to predict the users under different city state. And also from our results, we can see that for the crowd for the different dimensions of the context, it can encode different aspects or different state of the city. Like for the context of the dimension 4, it is very sensitive to such kind of events like the Obon festivals. It is Japanese holidays, and it is very sensitive. And some dimensions, it is less sensitive to such kind of events. It is more real-time mobilities, and we can see that this dimension does not change significantly during the Open Festival. And our results can show it will having a better prediction. And another works is used especially on the irregular mobility prediction is an online adaptive ensemble way. We train a different predictor, cluster level predictors that under different conditions. Like if we only focusing on the most recent, using the most recent 1 hour's data, we can train a predictor that is encoding the most recent or quite the drifting concept of the irregularity mobility. And from the historical data, we have, for example, weekday or weekends or New Year's or some big events, such kind of days, we train a separate predictors and combine it together for online predictions to handle the different kind of regularities in the mobility prediction task. And also for the users' intentions, we cooperating with Yahoo Japan, and we can having the people's searching queries logs, and we analyze how it is correlated with users' mobilities. And because from the raw trajectories of the users, we can hardly know that the user's intention. For example, if the user want to go to spring or going to a sightseeing place for traveling, it is very difficult to be seen from their trajectories before he went there. So in that case, we are combining the search queries to having a better estimations of the people's future movements. And we using the factorization machine models for modeling the spatial and temporal interactions in this work. So for this part, we have modeled the cluster level predictions that can predicting the users more larger scales movements. And for the second part, we show how it can be refined to the cross levels prediction to a fine-grained levels prediction. The main factors we take into consideration is the destination clusters, which is the 1 hours where this user will go, and their current location and the current time. And using these factors to generate queries to the history's trajectory database, and the samples with the similarities to find most similar trajectories that suitable for the current location and where the place will go and the current time condition, and to predict the history's trajectory as a prediction. And also for the history's trajectory database, because we have precise with trip segmentations and mode detections and do the map matching, so the trajectories we are having more semantics like which. It is not the GPS trajectories, but it is which road it is travels and which station it's passing by. Such kind of more rich traffic attributes can be predicted using this framework, and also our prediction results can show the very accurate predictions accuracy, and also our prediction can be aggregated to different application scenarios, like we can see road segments, the traffic volumes, or we can see how many people will transfer from one line to another line, and or the stay peoples in the within big interchange stations. Such kind of different requirements we can be solved in these methods. And also note that we are using the historical database for building for recombining that to generating our prediction results, and it can also be very easily for doing some simple simulations. Like we can add some conditions to our searching queries, like whether this railway is down, and we can if we want to simulate this railway is down, and then we can add these conditions, and then it will predict the trajectories that without using such kind of links. And for example, here is our prediction results. On normal day, many people will using the Musashino lines in Tokyo, which is ring roads in Tokyo. And if we want to predict what if the Musashino line stopped, we can using our framework adding the conditions and then generating the next 1 hour's mobilities that without using the Musashino line. And also the methods of recombining the historical database, we are the similar methods is also applied for simulating the human mobilities during the COVID-19, and we developing interface that for simulating how people's mobility in responses to different control policies of COVID-19, like telework or city lockdown, or setting some screening point. And then first simulate how people's mobilities will be in response to such kind of control policies, and then simulate how the disease is spreading in the city, and then we can evaluate the effectiveness of different control policies. And here is simple demos, like how we simulate people's how we simulate the disease spreadings under different control policies. And here is the interfaces of how we can set our control policies, like telecommunicating and screening point. And then here is for the if no control policies is applied, how the spreading change. And if the control policies is if the lockdown of this region, and how the disease spreading will change in response to that. Okay. So in summaries, it's our mobility digital twin systems. It combines mainly 4 parts. And for the data streaming parts, we can collecting the sensors data or the GPS trajectories at the larger scale. And for the logs data of the GPS trajectories, we make the processing of the map matching to build the map matched GPS database, and also to train cluster level predictors using the history's GPS data. And in the online parts, we make the 2 levels predictions, and first we predict the cluster levels, and then it can be refined using predict by retrievals ways that to predict the node levels prediction, and then it could be support different levels of the higher levels analysis. Okay, so that's all for. Thank you.